Today we're going to talk about concentration. Now, what that doesn't mean is for you to focus or, focus. That's a good thing to talk about. The concentration we're going to talk about is like if something's dilute or not dilute, concentrated, things like that. In layman's terms, or on the news, you might hear the terms ppm and ppb. Yeah. There's some good ppms out there. This is a good one. This ppm deals with parts per million or parts per billion. Now, if I had, say, 1 million particles, let's say I have a sample of drinking water, and in that you've got your million particles. Now, a lot of that is made up of H2O. Sometimes, like you may hear on the news, that there are acceptable levels of fecal matter in your drinking water. Typically, that's around 5 to 7 ppm. Okay? So in other words, for every million pieces or particles of water that we have there, 7 of those might be fecal matter. Okay? Now, that's what gives water flavor, right? Yeah?
No.
Exactly. So in other words, if you've ever drank distilled water, and I wouldn't recommend it because it has no taste. So if you like drinking spring water or the mineral water or whatever it is, generally they get that from a running stream. Very clean water. Now, it does have a unique taste to it. Why is that? Because there's moose urine in that. All right. Now, that won't be on the label or anything. But what's in the water to make it taste good is nature. Okay? So these are just terms I want you to be familiar with. You're not going to see them on the test. You'll see them often in news articles or other types of things that deal with people that are not chemistry related. Molarity, however, is the type of concentration that we will be talking about. Okay? So when we talk about molarity, we're talking about the number of moles of solute, the thing that's dissolved, in how much of the solvent. Okay? So typically it's moles over liters. So when you hear the term molarity, we're talking about a solution or the concentration of a solution. We'll always make sure that the value goes with the moles. So if I have, say, like a 2 molar solution, that means I have 2 moles in every liter of solvent. All right? We do represent that with the big M. So sometimes you might say, oh, that's mega. No, that's molarity. So the big M is molarity. What we don't want to do is confuse the molarity of a solution with the number of moles of a substance in a particular sample of that solution, because it's based on the volume of that solution. Okay? So again, here's an example that if I had a 2.25 molar solution, then I have 2.25 moles for every liter of that solution. If I'm giving you a volume that's not 1, and we know the molarity, I have this statement on here. If you know the volume and the molarity, always start with the volume. All right? Because again, molarity is moles over liters. That way we can cancel out liters and we'll have moles. So this is a really important statement. That's why those letters are much bigger. When we look at preparing solutions, this is our one time we get to write a sentence.
Never.
Okay? You'll get to do some math and then you'll get to write a description. In other words, what you're going to do is write a description that explains how to prepare the solution. Now, will you ever prepare one of these? Not in here. Maybe in AP I'll have you do one, but not in here.
Wait, what are we doing in AP?
Preparing solutions. Okay. Now, what we have to realize is that when we're preparing a solution, we have to have whatever our volume is. Okay. And it's not like making Kool-Aid, all right, where you take a gallon of water or 2 liters of water or what is it, quarts? What do you guys use nowadays? Quarts. Okay. I hate quarts. All right. So you take your quarts, whatever that is, all right, and then you add your, what is it, like 20 cups of sugar, and then you add your little Kool-Aid packet thing there. Now, in chemistry, we want to make sure that we have just enough water for whatever volume it is that we're making. So you don't start off with, like, if I'm making a liter solution, I don't start with 1 liter of water, because if I add some solid to that, what's that going to do to the overall volume? It'll increase it. So we want to make sure that we have just enough water for a total volume. All right, and we'll do that once we do some percent composition. All right, percent composition. Hopefully, the name says it for you. That if I have a substance, oh, I don't know, let's say that half of it is hydrogen, the other half is oxygen. What is the percent of hydrogen in the compound? 50%. All right. So we'll be doing some work with this to help us for the next topic, which deals with empirical formulas and molecular formulas. So we'll do some calculations with percent composition. And the name, I hope, is giving you enough information there. And when I do the math, that'll be a much better explanation than what this is. All right, let's look on page 9, about the middle. The first practice problem, it asks, how many moles of sulfuric acid, H2SO4, are contained in 3.5 liters of a 6.5 molar solution? Number 9, or page 9. It's about in the middle. Practice problem number 1. Now again, the question wants to know how many moles. So in this case, you were given the volume, which is 3.5 liters, and the molarity, which is 6.5 molar. If you know the volume and the molarity, in other words, again, you know these. Okay? Know the volume and the molarity. Always start with the volume. Always. Because again, molarity, which we just talked about a second ago, is moles per liter. And if we're looking for the moles, volume will always be in what unit? Liters, or it should get to liters. That way we can cancel the liters out using our factor labeling. So number 1, we have 3.5 liters. And the molarity, which is moles per liter. What we should never do is put big M in the factor labeling. Always use these units here. So mole per liter. So if I have a 6.5, or a 6.5 molar solution, what that means is I have 6.5 moles of my solute for every liter that I have in the solution. That's really important because the number will always go with the unit mole. Liter should always be 1. So we'll put liter down here and 6.5 up here. The liters cancel out, and whatever 3.5 times 6.5 is. Add not plus. Yeah, 22.75 or 22.8 moles. Okay. So again, really important. If you know the volume and the molarity, always start with the volume. Now sometimes I'll give it to you in milliliters. Be sure you convert the milliliters to liters and then go ahead and use the molarity. Number 2, what is the molarity of a solution that has 75 grams of calcium hydroxide dissolved in enough water so the total volume is 3.5 liters? In this case, we don't know this, we don't know the moles, and we're actually asked to calculate the overall molarity. My advice, build it, okay? So you have 75 grams, what is it, calcium hydroxide? Yeah, calcium hydroxide. Okay. So again, make sure you can still write those formulas. Find out how many total moles that is. So calcium is 40.08. And then we have 2 oxygens plus 2 hydrogen. Sure. Okay. Whatever that is.
You start memorizing these things.
What's that?
You start memorizing like the
After a while, yeah.
Yeah, I started memorizing them.
And like carbon and nitrogen.
So all that is 74 point
What's the subscript on hydroxide?
-1.
on here. That's 2.
Oh, I thought you meant like.
Sorry. Yeah. So near 0.96. Did I do that right? Yeah. So that's how many grams that is. So take 75 divided by that. A little greater than 1, right? So 1.01. So our molarity is equal to 1.01, whatever's in my calculator. And what was the total volume? 3.5 liters. Whatever that equals. 3.5. So, like 0.289 molarity.
That's
So that like whole thing up there was.
So this right here,
That's called 1.01.
right? This got me that,
We already know how to do that.
and then the 3.5 liters. We just divide that by that. Okay. So again, when you're looking at the molarity, be sure that you know how many moles we have. And sometimes I'll give you the moles, sometimes I'll just give you the mass. And if I've given you the mass, convert that. Okay. Let's take a look at the next one on page 10.
Is this our homework?
No, it's still another practice problem. This is your opportunity to write a sentence here. Bottom half of page 10, it says, give the directions for the preparation of 3 liters of a 1.5 molar copper sulfate solution. Okay. So, what we want to do is, I want you to be able to give me directions or instructions. Say if I ask you, okay, I want you to go into the chemical cabinet, which is on the other side of the building, about a quarter mile away from here, literally speaking. Get enough copper sulfate and make me a solution. So, in this case, do we know the volume and the molarity?
Yes.
Yes. So if you know the volume and the molarity, what do you start with?
The volume.
The volume. And we have 3 liters. This poor pen is about to die. It had a good run. That's okay. And the molarity is 1.5. So again, it's 1.5 moles for every liter. Now, and you haven't had an opportunity to do this yet, we will on the lab. I think we're going to have a lab next week. It's a Bunsen burner lab.
I don't like that.
No fire, don't get excited. Whenever we've had a chance to weigh something out, or if you've ever had a chance to weigh yourself out, what does the scale read? Pounds? What will our scales read in here? Grams, good. So, the balance doesn't read in moles, does it? Unfortunately? I don't think they have one of those yet. So that's why we always, as a good chemist, we always want to have one of these nearby. So, if I can't measure it out on a scale using moles, what do I need to convert this to?
Grams.
Good. So we've got to take our moles of copper sulfate, okay, and change that to grams. So in 1 mole of copper sulfate,
You gotta use that molarity.
Do we have to use that one number?
Yeah.
no, we're not using Avogadro's number today.
No.
But we will use your periodic table. So grab your periodic table. Unless you have all these masses memorized. And don't.
I only have some.
So copper is 63.55. Sulfur is 32.06.
There you go.
And oxygen is 16 each.
159.
I know it's oxygen.
I think I've seen.
You've seen carbon? Atta
Carbon
girl.
is 12.01.
And let's see here. So, and again, if you want to put the molar mass above, that's fine, just to speed things along. So the molar mass for copper sulfate is 159.61, and then we're just going to multiply it times 1.5.
366 still?
Not yet. Actually, no, not on this one, because we're going to prepare a solution.
So cross out moles and cross out liters.
Yes. So the moles are gone, the liters are gone, and we're left with grams. Okay. So now we have something that we could actually measure out. All right. So now what we're going to do, actually, let me go grab some here. Call it a volumetric flask, and It's rather expensive, actually. That's why I don't let you guys touch it. I don't actually let my AP kids touch it either. But there's a single line, and I don't, you might be able to see it if you're this close against my dark shirt. The dark line there. Very, very, very discreet here. What this line indicates is it's actually a certain volume. Let's do it for the camera. So this is a volumetric flask. Okay. And there's a line right here. Okay. We'll put that there. So what we need to do is, we know we need to put 718 grams, and here's some copper sulfate. I'm not going to mix it up, but that's what we're going to use for our lab as well. But we'll place 718 grams of our copper sulfate in our volumetric flask. Now, what we don't want to do is add 3 liters of water. What we're going to do is we're going to add just enough water to get the level of the water to that line. And we'll shake it up. So what that ensures is that we have 1.5 moles for every liter. Isn't that cool? So here's our instructions. You're going to, here's our sentence, and hopefully I won't make it a fragment. You'll place 718.245 grams, and be sure you tell everybody what it is. So 718.245 grams of copper sulfate, actually copper 2 sulfate.
Put the 2 in? Oh.
No, just CuSO4 is fine.
Sorry.
In a volumetric flask. What do you think a volumetric flask is?
That.
Okay. So it's very, very specific for its purpose. You don't store things in this, you just measure and then put that in something else. So we're going to place 718.245 grams of copper sulfate in a volumetric flask. Then add enough. And this is important. These 2 statements, we're going to add just enough water so that the total volume is what?
3
liters.
Okay.
So here are some really important components. Okay. The things that I have underlined, you must have that in your statement. Okay. You must have that in your statement. How you want to augment the other things is up to you. Okay. So we need to tell everybody how much of what it is. Be sure to add just enough water so our total volume is 3 liters.
Will it always be that 3 liters?
No, the volumes will change.
Okay.
Yeah, we'll do another example here. Okay. And hopefully that's not a run-on or a fragment or whatever. Yeah.
So all of these will basically look like that, except for the volume, and that will change.
This will change, and that should change.
But that's the setup of the sentence.
Perfect.
Okay.
Yep.
And it won't ever change.
What's that?
It won't ever change. The
It'll always be a voluminous.
Well, I mean, depending on your flair and your style and how you want to present, that's up to you. But be sure you have those components in there. All right. Let's look at one of your homework problems, the ones here, before we do percent composition. Let's find an ugly one.
1F.
F, you want to go right for the jugular there?
Yeah.
It's the last one, so that means it's not my hard.
I don't necessarily think it's the hardest one. Let me look real quick.
Take a look.
E and F definitely are interesting.
I think we should do both.
Nah, we'll do one. I want you to have something to do.
Mini, 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 mo.
How about we do E because there's milliliters in there?
That's easy though.
That's fine. No, let's do that. Because then you gotta
All
convert.
you have to do is convert it to liters.
Alright, we'll do E just because I'm nice. Alright, 1E. Try. Alright, so the question wants to know what molarity of a sodium hydroxide solution where we have 10.3 grams of sodium hydroxide is dissolved in 300 milliliters of water. Wow, this is a tough one. What do I do? Convert? Convert what?
Start with the grams thing to do with yeast.
Okay. Now, can I show you a trick?
Yeah.
Now, you don't have to do this. Remember what I did over here where I built the molarity, where you take, again, molarities, moles per liter, and you can find the moles and then find the liters in two separate equations and put them together. You can still do that. Here's another option.
It's a double.
I know, right? Now, remember, convert one thing before you start converting the other.
Yeah.
Okay? Do I not have, technically speaking, we're going to convert the grams to moles. Okay?
Can we do the other one?
You could do it your way. Do it your way, Beth, and see what you get.
No, I don't want to. I'll just go.
Oh, Beth, since you're unsure here, what do you want to convert, the grams or the milliliters first? Okay. So where do the unit milliliters go? Here or here?
Huh?
Where do the milliliters go? Down or up? Why?
Because that's how you taught us.
So they cancel out. Very good. So we don't have milliliters squared, right?
Right.
Yeah. So what goes on the bottom then? Good. Which one's bigger? Huh?
Put one on the bottom.
Okay. What on top?
10 to the something. Third, I think.
10 to the something. Gotcha. So milliliters are gone. Ooh, this is looking good.
Am I done?
No.
No. Oh, hang on, I've read that.
We'll give Beth a break here.
I'll do it.
Of course you would.
Caleb, what do I do next?
You take the grams and you find the molar mass of the element.
Good. Okay, so sodium hydroxide. Yeah, it's just what we've been doing. Nothing new here. So we have one sodium, and that's what? 22.99?
Yeah.
And oxygen, 16. Hydrogen.
1.08.
And I think that's like 39 point something.
998.
Yeah. All right. So now we've gotten rid of our grams. What units do we have left?
Moles. What we need.
Moles per liter, right?
Yeah. I thought you were just talking about the top.
Oh, my bad, my bad.
Grams.
My bad. So, divided all that. Let's see what you guys get here. Oopsie. And be sure that, remember that, use your parentheses on the bottom here, so you don't get something weird.
This calculator
I bet it's the operator.
sucks. No, when you raise it to an exponent and then you try dividing something.
Oh yeah, yeah,
it keeps it up
your
there,
pinky
that
over there.
exponential.
Anybody get a number here?
0.700.
Anybody else get that?
Hold on.
Keep it on cake.
Let's make sure I typed that in right. Yeah,
I got 0.86.
that's what I got. Try it again, Jeremiah. Or were you doing mental math there? Anybody else get
858.
5.8? Yeah.
But then,
What?
never mind. Seriously.
So, this is saying that we have 0.858 moles for every liter of solution. Is that correct?
Yes.
Good. Okay.
Yeah.
All right. So I'm willing to bet that that's not going to be too difficult.
Does it say that on our notes somewhere?
It does.
Moles and molarity. Moles over the liter.
All right, let's look on page 12, since you guys already have the blanks for percent composition. Or actually no number. On page 12 at the bottom there, it says determine the percent composition for each of the following elements in magnesium nitrate. Ooh, magnesium nitrate. Let's make sure we're writing that correctly. So magnesium and then nitrate is what?
NO3 -1.
Good,
You have to have 2 of those. But
good, okay. So there's our compound for magnesium nitrate. If I want to find the percent of each of these, I want to find it by mass. Okay, whenever we do percent composition, it's always by mass. So let's first of all find out the total molar mass of this thing. So magnesium, 24.3.
Holy moly, Craig, you're
Sorry,
memorizing these.
you use it enough, you'll remember these. And then we have how many nitrogens? 2. And each one's 14.0.
I got that.
How many oxygens do we have?
6.
And
16.
oh, hey. So we'll get a total mass there. 1 mole of magnesium nitrate has a molar mass of this, and we don't want to round that. Okay, don't round that, because we're going to do something with it. Now, I want to find out if for percent composition, what is my percent of magnesium, my percent of nitrogen, and my percent of oxygen. Kill 2 of them. How can I do that? And again, we really haven't talked about it. How can I find out the percent of magnesium in this compound?
Take the total grain.
Total mass of magnesium. So if I had 1 mole of magnesium nitrate, how many grams of magnesium are in that 1 mole of magnesium nitrate? Yeah, 24.3.
Divide that by the big number.
Times 100. Right?
Yeah.
Oh, I thought we'll do that.
So times 100. Make sense? And then nitrogen. All right, so
Same thing,
same thing.
but you have to multiply by 2.
Oh, because there's 2 of them.
Yeah.
So it's the total mass within that compound. So in this case, it's 2 times the 14.01. Some of you may know it as 22.0, 24, 20, 28.02.
You okay?
Don't get old. Don't get old. And whatever that equals. And then the last one, the oxygen, 6 times the 16. Whatever that equals. Now, this is a crazy question, but what should all 3 of these add up to be?
100.
Got it. Good.
Wait, what? They should be what?
I don't know.
100?
148. 100%.
Oh, I was thinking 148.
Uh-huh.
Is it? Is that right? Right.
Oh, I'm sorry, what?
What are they supposed to add up to?
100.
Oh, yeah. Confused me, but it's okay.
So 16 point, and we'll go 2 decimal places.
Oh, wow.
We really don't want to round too much here, or else if we round it too much, then it might not work out as well as we want. Or we might get a little over, a little under.
Which is completely okay,
I
right?
don't know. So 37.78. And actually rounding by 2 places might be dangerous. Now, tomorrow.
100.08.
What?
What?
That's what I got when I added them all up.
All these up?
Yeah.
No. I won't believe it. There's no way we rounded that bad.
Wait, what did you get?
100.08.
That's that bad?
16.3 plus 37.78.
Mr. Craig, I think you got the second one.
Yeah? Oh yeah, that's way off.
Yeah.
2 times 14.01.
It should be
Divided by-
18.89.
I concur. Holy cow. Oh, so you're not doing your work over there, Vanessa? Is that what I'm seeing? Alright. Thought it was easy?
That's what I thought too.
What?
I got that, and then you switched, and I was like, okay, so maybe my math is wrong. But
So you're just gonna sit there quietly and not say a word and...
I mean, you were gonna see a mistake eventually. I was just waiting.
Look at that. What's that add up to?
Oh,
We're in Indiana. That's 100. Okay.
Mr. Craig, on Blue, they talked about how Indianapolis was the Paris of Indiana.
Paris of Indiana. Oh, Lord.
I was like, what the heck?
Exactly. All right, let's do another on page 13. Do you guys have difficulty with that? I really don't want to take your homework away from that. Let's look at 2D or 2E. Which one do you want to look at?
2E, it's bigger.
Okay. Now remember the bold there says determine the following samples are the same compound. Well, let's look at 2E since it seems like nobody else wants to say anything. We have a sample. Sample 1 is 75 grams containing 20.5 grams of carbon. So we have 20.5 grams of carbon and 54.5 grams of oxygen. Okay? That's sample number 1. Okay. Sample number 2 says that we have 157 gram sample containing 67 grams of carbon and 54. Wait a minute, no, I'm looking 90. Yeah, can't look back and forth. 90 grams of oxygen. Okay, and the question wants to know: determine the following samples if they are the same compound. So, are these the same compound? Well, let's do this. What is this plus this?
Wait, I'm confused on what you're saying.
The question is,
That'd be.
are these the same
Well, no,
compounds?
they're different numbers.
What's a better way to check?
Find the percentile.
I don't
Yes,
understand.
true, they are different numbers.
So they can't be the exact same.
Well, we don't know yet.
Wow.
What can we do to see if these
Okay,
are the same?
clearly 54 plus 20 is like,
They're the same.
or whatever.
Oh,
It's gonna
ow.
be like 76 or something. But
Okay.
then like
75.
90, that's already over.
Okay, let's do it this way. Let's find out the total mass, right? Which is 75 grams of this carbon oxygen compound. Okay? And we're not finding out what X and Y are today. We're not finding that. That's tomorrow. Okay? And then let's say that this is 157 grams of this carbon oxygen compound. Everybody follow me so far? What can we do to determine if this is the same? Yeah, Jeremiah.
We could find the percentage.
Yeah.
Find a percent. Good. So I know that I have 20.5 grams of carbon in this 75 gram sample. So we'll do 20.5 divided by 75, which is 27.3 repeating. Okay, that's percent. Now, let's use our heads here. Do we need to find out the percent for oxygen if we want to compare these two?
Just
Why?
100 minus 20.
No, wait. Hold on. Why?
The amount of carbon would be the same as the other one if they were equal.
Correct. So we can check just the percent for the carbon. If you're just dying because you have nothing better to do in your life, then you can find out the percent of oxygen. But if you want to find if these are the same, then just check one of them. If they're the same percent, are they the same?
Wait,
Yep.
wait.
If they're different percents,
Are different percent. Do you have to check the oxygen?
no, because there's only two things. If they're not the same percent, they can't be the same
Yeah,
compound.
but I mean, if they're the same, do you have to check the oxygen?
No,
You just know they're different. I mean, wait.
Same.
You just know they're the same.
correct. So let's do that. So 67,
They ain't the same.
Do you get
they
what I'm
ain't the
saying?
same.
Do you get what I'm saying?
Yeah, it's unnecessary. You can do it. I'm not saying you can't.
I mean, I don't want to, but I'll have to.
So in this case, it's 42.7. So looking at these two samples, they are not the same. Okay. Now, tomorrow we'll actually find out what the X and the Y are, or the next time we meet. But today we're just looking to see, are these the same thing? So for E, for D, do you think you could figure that out?
Not at all.
Exactly. So your homework, the 1s and the 2s tonight.